Assalamualaikum. So today we would learn about the integration of rational function method 4. So look at this comics cartoon. If we have the integral equation x squared multiplied with x1 minus x0 plus x squared multiplied with x2 minus x1 plus dot 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 plus x squared and xn minus xn minus 1, what do we get? Confused? The student would answers the question confused. So integration of rational function, we have three types of it. So rational is divide the function px divided by qx. So in this section we will investigate about the improper rational function whose denominator cannot be factorized, rational function whose denominator can be factorized. Right? So improper rational function. When you have the function px over qx is an improper rational function if the degree of the numerator is larger than or equal to the degree of denominator. So this is numerator, this is denominator. So if the integrand is an improper rational function, then long division or algebraic manipulation needs to be performed to change the integrand to a proper rational function. Alright, so look at the example from YouTube. So you can see the YouTube also for the improper integral.
Try to evaluate the following integral. Assuming you've had a go at it, so let's work through this together. If at any point you get inspired, always feel free to pause the video and continue on with it on your own. So the first thing that might have jumped out at you, we have a rational expression. The degree in the numerator is the same as the degree in the denominator, so maybe a little bit of algebraic long division is called for. So let's do that. Let's take x squared minus 1. Let's take x squared minus 1 and divide it into x squared, a different color, divided into x squared plus x minus 5. So x squared plus x minus 5. And so let's look at the highest degree terms. How many times does x squared go into x squared? Well, it goes one time. Color. It goes one time. 1 times x squared minus 1 is just going to be x squared minus 1. And I subtract this green expression from this mauve expression, or I can just add the negative of it. So let me just take the negative of it. So it's going to be negative x squared plus 1. And we're going to get the x squared minus x squared is 0, so those cancel out. And we're going to be left with x. And then negative 5 plus 1 is negative 4. So we have x minus 4 left over. So we can rewrite the expression that we're trying to find the antiderivative of. We can rewrite it as 1 plus x minus 4, 1 plus x minus 4 over x squared minus 1 over x squared, maybe I'll do that in purple colors, over x squared minus 1. So we did one thing. Now we have a lower degree in the numerator than we have in the denominator. And obviously this is fairly straightforward to take the antiderivative of. But what do we do now? It's not clear. If we look at x squared minus 1, its derivative would be 2x, which is the same degree as this, but it's not x minus 4, so it doesn't look like substitution is going to help us with this. So what can we do now? And now we can take out another tool in our algebraic toolkit. We can essentially do, or we will do, partial fraction expansion, which is essentially writing this as the sum of two rational expressions that have a lower degree in the denominator. So what do I mean by that? So this term right over here, x minus 4 over x squared minus 1, we can rewrite that as x minus 4 over, instead of x squared minus 1, we can factor this. This is x plus 1 times x minus 1. Let's write that. This is x plus 1 times x minus 1. When we think about partial fraction expansion, we say, okay, well, can we write this as the sum of something, let's call that a, over x plus 1 over x plus 1 plus something else, let's call that b, plus b over x minus 1. Can we do that? And to attempt to do that, if we had to just add these two things, what would we get? Well, we would find a common denominator, which would be x plus 1 times x minus 1. And so you would have, and if any of this looks unfamiliar, I encourage you to review the videos on partial fraction expansion, because that's exactly what we're doing right over here. But this would be equal to, if you were to add the two, your common denominator would be the product. So it would be x plus 1, x plus 1 times x minus 1, x minus 1. And then, so the first term, I would multiply the numerator and the denominator times x minus 1. So a times x minus 1. A times x minus 1 plus b, the second term, I'll multiply the numerator and denominator times x plus 1 times x plus 1. And so what do we get? This is going to be equal to, ax, maybe I'll do this all in one color. This is going to be equal to ax minus a plus bx plus b plus bx plus b, and then all of that over this stuff right over and over again. Let's copy this. So copy and paste. Set over and over again. We have that over that. Let's see, so now we can group the x terms, so we can rewrite this as, if we take ax plus bx, that's going to be a plus b times x, and then we have a negative a, and so plus b minus a, and I'll just put parentheses around that so I group these constant terms, and then all of that's going to be divided by, that x plus 1 times x minus 1. And so now this is the crux of partial fraction expansion. We say, okay, we kind of went through this whole exercise on the thesis that we could do this, that there is some a and b for which this is true. And so if there is some a and b for which this is true, then a plus b must be the coefficient on the x term right over here. So a plus b must be equal to 1, must be equal to this coefficient, and b minus a must be equal to the constant, must be equal to negative 4. Or if they are, then we will have found an a and a b, so let's do that. So I'll do it up here since I have a real estate. So a plus b is going to be equal to 1, and b minus a, or I can write that as negative a plus b, is equal to negative 4. See, we could add the left-hand sides and add the right-hand sides, and then the a's would disappear. We would get 2b is equal to negative 3, or b is equal to negative 3 halves. And then a is, we know that a is equal to 1 minus b, which would be equal to 1 plus 3 halves, since b is negative 3 halves, which is equal to 5 halves. A is equal to 5 halves, b is equal to negative 3 halves. And just like that, we can rewrite this whole integral in a way that is a little bit easier to take the antiderivative, or this whole expression, so it's easier to integrate. So it's going to be the integral of 1 plus a over x plus 1. A is 5 halves. So I could just write that as, write it this way, 5 halves times 1 over x plus 1, and I wrote it that way because it's very straightforward to the antiderivative of this. And then plus b over x minus 1, which is going to be negative 3 halves. So let's try this, minus 3 halves times 1 over x minus 1. That was this right over here. Yes. Notice all I did is I took this expression right over here, and I did a little bit of partial fraction expansion to these two expressions or terms right there. And now it's fairly straightforward to integrate this. Antiderivative of 1 is just going to be x. Antiderivative of 5 halves, 1 over x plus 1 is going to be plus 5 halves. The natural log of the absolute value of x plus 1. We were able to do that because the derivative of x plus 1 is just 1, so the derivative is there so that we can take the antiderivative with respect to x plus 1. You could also do substitution like we've done in previous examples. U is equal to x plus 1. And over here, this is going to be minus 3 halves times the natural log of the absolute value of x minus 1. Let's say in exact logic how we would take the antiderivative there. And of course, we cannot forget our constant. And there we have it. We were able to integrate. We were able to evaluate this expression.
Okay, so this is the example. So you can see here, this is long division. You already know what long division, isn't it?
Try to evaluate the following.
So we look at here. So this is the example when we have x cubed plus x over x minus 1. So you can use long division. You divide and then you get x squared plus x plus 2 plus 2 over x minus 1. So then you can solve it. So to be x cubed over 3 plus x squared over 2 plus 2x plus 2 ln x minus 1 plus c. Okay? This is the next example when you have x plus 1 over x minus 1, the same degree for numerator and denominator. So you can use the algebraic manipulation. You can see here. So when you have x plus 1, 1 is equal to 2 minus 1. So divide by x minus 1, so x minus 1 plus 2 over x minus 1. So x minus 1 over x minus 1 will be equal to 1. So plus 2 over x minus 1 here. Then you can integrate both sides. So equals to 1 to be x, 2 over ln, so 2 over x minus 1 to be 2 ln x minus 1 plus c. Alright. So next, a rational function whose denominator cannot be factorized. Completing the square is a technique that is suitable to evaluate an integral involving quadratic expression ax squared plus bx plus c, where a not equal to 0, b not equal to 0. For rational function px over qx, completing the squares is used if qx cannot be factorized. Okay. So look at the example. When you have 1 over x squared minus 2x plus 5, 1 over. So you need to use the completing the square. Completing the square formula is x minus b over 2 square minus b over 2 square plus c. So this is coefficient a is equals to 1, coefficient b equals to negative 2, coefficient c is equals to 5. So here 5. So you use the formula, you will get x minus 1 power of 2 plus 4. Solve the integrals. So you can find here x minus 1. So you need to let u is equals to x minus 1 differentiate to be dx. So 1 over u squared plus 4. So u squared plus 4 is tangent inverse. So you get 1 over 2 tangent inverse u over 2 plus c. So a is equals to 2 square. So you get 1 over a, u over a. Okay.